This presentation is about the partitions of unity on smooth manifolds. We will provide necessary definitions and provide the proof to the theorem. The assumed background is charts, atlases, smooth structures, and smooth maps. Smooth structures are defined locally via coordinate charts, but global objects are what we need. On the two-sphere S2, each coordinate patch admits the standard Euclidean metric, the sum of squares of coordinate differentials pulled back to the patch. But two different charts produce two different formulas, and those formulas have no reason to agree on the overlap. The Gluing Lemma, which assembles local smooth maps into a global one, requires exact agreement on overlaps. Chart-by-chart constructions never satisfy that requirement. The problem is concrete. If you want a Riemannian metric on S2, you have local metrics. G alpha, defined on each chart domain U alpha. Each G alpha is a smooth, symmetric, positive, definite 2-tensor on U alpha. On the overlap of U alpha and U beta, G alpha and G beta are written in different coordinates, and they are unequal as bilinear forms. Direct gluing is therefore impossible. Partitions of unity resolve the difficulty. Instead of asking local objects to agree, we introduce smooth weighting functions, one for each chart, that are non-negative, sum to 1 at every point of the manifold, and have their support contained inside the corresponding chart domain. A global metric is then the weighted sum G equals the sum over alpha of psi alpha times G alpha. Each term, psi alpha times G alpha, is a smooth tensor on all of M, extended by 0 outside the support of psi alpha, which is contained inside the chart domain U alpha. So the sum is smooth by local finiteness of the supports. The weights summing to 1 guarantees positive definiteness. For any non-zero tangent vector, the weighted sum of positive values with non-negative weights summing to 1 is strictly positive. This construction succeeds by avoiding the gluing lemma entirely, so stating that lemma next shows where chart-by-chart metrics fail it. The gluing lemma states precisely the condition under which local smooth maps assemble globally, so that the condition it fails to satisfy for metrics is visible. The lemma applies when we have smooth maps F alpha from open sets U alpha to a smooth manifold N, and these maps agree exactly on every pairwise overlap. F alpha restricted to the intersection of U alpha and U beta equals F beta restricted to the same overlap. Under this exact agreement hypothesis, the maps assemble into a unique smooth map F from all of M to N. The proof rests on a single observation. The compatibility condition on overlaps means the collection of local maps is consistent. For any point P in M, any two charts U alpha and U beta containing P assign the same value, namely F alpha of P equals F beta of P. So the rule F of P equals F alpha of P for any alpha with P in U alpha is well defined as a set map. The choice of alpha does not matter. Smoothness follows because smoothness is a local condition. Near any P, choose one chart U alpha containing P. On that open neighborhood, F equals F alpha, which is smooth by hypothesis. Since P was arbitrary, F is smooth on all of M. Uniqueness is immediate. Any G with G restricted to U alpha equal to F alpha agrees with F at every point of every U alpha, and therefore also at every point of M. This agreement on open overlaps is essential, since pointwise agreement at overlap points is not enough. Define F plus from the interval 0 to 1 by F plus of x equals x, and F minus from -1 to 0 by F minus of x equals -x. Both are smooth, and they agree at the single overlap point x equals 0. Both send 0 to 0. Their pointwise extension is F of x equals the absolute value of x, which is continuous, but fails to be differentiable at the origin. Exact agreement at a single point is not sufficient. The gluing lemma demands exact agreement as smooth functions on an entire open neighborhood of each overlap point. For chart-by-chart constructions, such as Riemannian metrics, even this weaker pointwise agreement fails. The metrics G alpha and G beta are expressed in different coordinate systems on the intersection of U alpha and U beta and need not coincide as bilinear forms, which is why the gluing lemma cannot be applied, and partitions of unity are required instead. The right branch is F plus of x equals x, defined on the closed interval 0 to 1. It is a smooth function on its domain. Every derivative exists and is continuous. The derivative of f plus is identically 1 on the open interval. The left branch is f minus of x equals -x, defined on the closed interval -1 to 0. It too is smooth on its domain, with derivative identically -1 on the open interval. Both branches are smooth functions individually. At the overlap point x equals 0, both send 0 to 0. So the gluing lemma hypothesis of pointwise agreement on the overlap is satisfied. The origin is the single overlap point. Both f plus and f minus evaluate to 0 there. The pointwise agreement condition is met, yet the gluing lemma for smooth maps requires agreement as smooth functions on an open neighborhood of the overlap, not merely at a single point. Pointwise agreement at one point carries no information about derivatives. The derivative of f plus at 0 is plus 1, the slope of the right branch. The derivative of f minus at 0 is negative 1, the slope of the left branch. These are the one-sided derivatives, and they are unequal. For a function to be differentiable at a point, the left-hand and right-hand derivatives must agree. The limit of the difference quotient from the left must equal the limit from the right. Here the left-hand derivative is negative 1, and the right-hand derivative is positive 1. They differ by 2. The two tangent direction vectors at the origin point in different directions, making the failure of differentiability geometrically immediate. The arc between the two slope arrows marks the angle of disagreement at the origin. Because the one-sided derivatives are unequal, the two-sided derivative f prime of 0 does not exist. The assembled function f of x equals the absolute value of x is continuous. It is the pointwise extension of the two branches, but it is not differentiable at 0, and therefore not smooth. The gluing lemma for smooth maps is inapplicable here precisely because agreement at the single overlap point 0 is not agreement as smooth functions on any open neighborhood of 0. On every such neighborhood, the derivatives disagree. This is the obstruction that partitions of unity are designed to circumvent, since assembling infinitely many local pieces into one smooth function only works when the piece's supports are locally finite. An infinite sum of smooth functions is smooth if and only if the support sets are locally finite. The condition determines when the global sum reduces locally to a finite sum. A collection of subsets of M is locally finite if every point of M has a neighborhood that intersects only finitely many sets in the collection. When the collection of supports is locally finite, near each point of M the sum has only finitely many non-zero terms, so it is locally a finite sum of smooth functions, and finite sums of smooth functions are smooth. Since smoothness is itself a local property, the global sum is smooth. Fix a smooth bump function, phi supported in the closed interval negative 1 to 1, with phi of 0 equal to 1. Set Si of x equal to phi of ix divided by I factorial. For each Si is non-zero in a neighborhood of 0. Specifically, Si of 0 equals 1 over j factorial, which is positive. So at the origin, infinitely many of the functions Si are simultaneously non-zero, and the collection of their supports is not locally finite at 0. The sum may still be smooth, but verifying smoothness requires uniform estimates on all derivatives, which is considerably more work. Local finiteness of the supports is the structural condition that makes smoothness of the sum immediate, without any further analytic work. The partition of unity construction is designed to satisfy it by construction. This gap structure between overlapping supports is most transparent in a concrete example on the real line. A collection of open intervals sits on the real line. The interval ij is defined as the open interval from negative 1 over j to 1 over j. So I1 is the interval from negative 1 to 1, I2 is the interval from negative 1 half to 1 half, I3 from negative 1/3 to 1/3, and so on. Each ij is the support of some smooth function on the real line. The function is non-zero exactly on ij and 0 outside. The intervals are stacked vertically here so that all of them are visible simultaneously. They all live on the same real line, centered at the origin. To test local finiteness at the point p equals 0, we ask, does every neighborhood of P meet only finitely many of the intervals ij? The yellow rectangle is a test neighborhood of P, an open interval centered at 0. At its current width, it already intersects all 8 displayed intervals because every ij contains 0 in its interior. The counter shows how many supports the neighborhood hits. Shrinking the neighborhood reduces its width, but the count does not drop, because every ij, no matter how small, still contains 0. The interval ij has half-length 1 over j, so 0 is always in its interior for every I. Shrinking further to a very small neighborhood still hits every single interval, because 0 belongs to ij for all I simultaneously. No neighborhood of P equals 0, however small, meets only finitely many of the supports I1, I2, I3, and so on. This is the definition of failing local finiteness at P. There is no neighborhood of P that intersects only finitely many members of the collection. The collection of intervals ij is therefore not locally finite at the origin. A second collection looks different. 4 intervals, each of width 8/10, centered near the integers 0, 1, 2, and 3, with gaps between consecutive intervals. The key structural difference is those gaps. Consecutive supports do not accumulate at any single point. Every point on the real line has a neighborhood small enough to miss all but at most 1 or 2 of these intervals. Because the gaps between supports have positive width, so a sufficiently small neighborhood fits inside one gap and intersects at most the adjacent supports. A test neighborhood placed at any point stabilizes quickly. As it shrinks, the count of supports it intersects drops to a fixed finite number and stays there. At a point inside a gap between 2 supports, the neighborhood eventually misses both adjacent supports entirely, and the count drops to 0. At a point inside one support, the count stabilizes at 1. This is exactly what local finiteness requires. For every point P, there exists a neighborhood of P that intersects only finitely many members of the collection. And in this case, the finite number is at most 2, independently of where P is placed. The gaps between supports are the geometric mechanism that makes local finiteness hold. This gap mechanism is exactly what paracompactness will guarantee in general. A collection of subsets of a topological space M is locally finite if every point of M admits a neighborhood that intersects at most finitely many members of the collection. An open cover V of M is a refinement of an open cover U if every member of V is contained in some member of U. Each smaller piece lies inside some larger piece. A topological space is paracompact if every open cover admits an open, locally finite refinement. Compactness is strictly stronger. It requires that every open cover have a finite subcover, which means the refinement itself is finite. Paracompactness only requires a locally finite refinement, which may still be infinite. The key example is Rn. It is not compact. The open cover by unit balls centered at integer lattice points has no finite subcover since Rn is unbounded, but it is paracompact, because that same cover by unit balls is already locally finite. Any bounded neighborhood meets only finitely many unit balls. Every topological manifold is paracompact. Given any open cover and any basis for the topology, it produces a countable, locally finite open refinement consisting entirely of basis elements. The proof relies on 2 properties of manifolds. Second, countability. This provides a countable basis for the topology. Local compactness. When combined with second countability, this guarantees the existence of an exhaustion by compact sets. The proof constructs the refinement explicitly. It uses the compact exhaustion to slice the manifold M into compact annular pieces and then applies a finite cover to each piece. Because these annular pieces have bounded overlap, the resulting overall refinement is guaranteed to be locally finite. This is the formal statement of what was just outlined. For any open cover and any basis, a countable, locally finite refinement by basis elements exists. The explicit construction of that refinement using a compact exhaustion is the proof that follows. Since M is a second countable locally compact Hausdorff space, it admits an exhaustion by compact sets, a sequence K1, K2, and so on of compact subsets of M with M equal to the union of all Kj, and each Kj contained in the interior of Kj plus 1. This is a standard result. One can construct the exhaustion by taking a countable basis of precompact open sets and building Kj as a union of finitely many basis elements whose closure is compact, growing the union at each step to cover the previous compact set. The key consequence is that M decomposes into compact annular pieces, Vj equal to Kj plus 1 minus the interior of Kj, each sitting inside an open shell Wj equal to the interior of Kj plus 2 minus Kj minus 1. These shells have limited overlap. Wj and Wj prime are disjoint whenever the indices j and j prime differ by 3 or more. Each stated property can be verified directly. Vj is compact because it equals Kj plus 1 intersected with the complement of the interior of Kj, a closed subset of the compact set Kj plus 1, and a closed subset of a compact set is compact. Wj is open because it is the intersection of the open set interior of Kj plus 2 with the complement of Kj minus 1, which is open since Kj minus 1 is compact and hence closed in the Hausdorff space M. Vj is contained in Wj. Any x in Vj lies in Kj plus 1, which by the exhaustion property is contained in the interior of Kj plus 2, placing x in the first factor of wj, and x does not lie in kj minus 1, because kj minus 1 is contained in the interior of kj by the exhaustion, while x is not in the interior of kj by definition of vj. For limited overlap, if j prime is at least j plus 3, then kj prime minus 1 contains kj plus 2, since j prime minus 1 is at least j plus 2, and the exhaustion sets are nested. So wj prime is contained in m minus kj prime minus 1, which is contained in m minus kj plus 2, but wj is contained in the interior of kj plus 2, which is disjoint from m minus kj plus 2. To construct the refinement, for each j and each x in Vj, choose a member xx of the given open cover that contains x, then, using the basis b, choose a basis element, bx with x in bx, contained in xx intersected with wj. Such a bx exists because xx intersected with wj is an open neighborhood of x, and any basis element of b contained in an open set and containing a given point can be found by definition of a basis. The collection of all bx for x ranging over Vj is an open cover of the compact set Vj, so it has a finite subcover, which we call Fj. The union over all j of the finite subcollections Fj is the desired refinement. It is countable, being a countable union of finite sets. It consists entirely of basis elements. It covers M because the annuli Vj cover M, and it refines the original cover because each bx was chosen inside some xx. Local finiteness, take any p in M and choose M large enough that p lies in the interior of Km. Possible because the interiors of the Kj cover M by the exhaustion property. A member Bx of Fj can only meet the interior of Km if the corresponding shell Wj meets the interior of Km. Now Wj is contained in the complement of Kj minus 1. For Wj to meet the interior of Km, we need the interior of Km to not be contained in Kj minus 1, which requires j minus 1 to be at most m, that is, j is at most m plus 1. For j greater than m plus 1, wj is disjoint from the interior of Km. Therefore, the interior of Km, an open neighborhood of P, meets only members from f1 through fm plus 1, which is a finite union of finite sets. Therefore, it's finite. With local finiteness established at every point, this completes the proof that every topological manifold is paracompact. This finite overlap argument has a direct geometric picture in the annular shells the exhaustion produces. The manifold M is exhausted by a nested sequence of compact sets K1, K2, and so on, each one contained in the interior of the next, with their union covering all of M. The annular region Vj is defined as Kj plus 1 minus the interior of Kj, the thin shell of new material added at each stage of the exhaustion. Each annulus Vj sits inside a slightly larger open shell Wj obtained by thickening the annulus radially in both directions. The key structural property is limited overlap. Shells Wj and Wj prime are disjoint whenever the indices j and j prime differ by 3 or more. A point P lying in the annulus V2 has a small neighborhood that meets only finitely many of the shells. In this case, exactly the 3 shells W1, W2, and W3. This proof used 2 properties of locally finite collections without proving them. Closures stay locally finite, and closure commutes with union. First, if a collection is locally finite, then the collection of closures of its members is also locally finite. So, replacing sets by their closures preserves the local finiteness property. Second, for a locally finite collection, the closure of the union equals the union of the closures. This second property fails for arbitrary infinite collections. The collection of open intervals 0 to 1 over n for n equal to 1, 2, 3, and so on has union equal to the open interval 0 to 1, with closure equal to the closed interval 0 to 1. While the union of the individual closures is the half-open interval 0 to 1, including 0 but excluding 1, those 2 sets differ. Local finiteness is the precise condition that allows the passage from the closure of a union to the union of closures. Let's prove part A. Let P be any point of M. By local finiteness of X, there is a neighborhood W of P that intersects only finitely many members x1 through xk of X. The claim is that W meets the closure of xj only if W meets xj itself. To see this, suppose the closure of some x in X meets W at a point Q. Since Q lies in the closure of X and W is an open neighborhood of Q, every open set containing Q meets X, so in particular, W itself meets X. Contraposing, if W does not meet X, then W does not meet the closure of X. Therefore, W meets at most the closures of X1 through Xk, establishing that the collection of closures is locally finite. Now let's get to part B. The inclusion of the union of closures inside the closure of the union holds for any collection, not just locally finite ones. Each X bar is a closed set contained in the larger union, and a closed set is contained in the closure of any larger set. For the reverse inclusion, let P lie in the closure of the union of all X in X. By part A, there exists a neighborhood W of P that meets only finitely many closures, say X bar 1 through X bar k. Since every open neighborhood of P must meet the union, P being in its closure, W meets X1 union through Xk. Therefore, P lies in the closure of the finite union X1 through Xk, and closure distributes over finite unions. The closure of a finite union equals the union of the closures. This places P in X bar 1 union through X bar k, and hence in the union of all X bar for X in X. The two inclusions together give equality. Property B will be used in the partition of unity proof, where the support of each normalized function must be identified as a union of closures of balls. Balls the regular coordinate ball construction supplies. A subset B of a smooth n-manifold M is a regular coordinate ball if there exists a coordinate ball B prime strictly containing the closure of B, a smooth coordinate map phi from B prime into Rn, and radii 0 less than R prime, such that phi maps B onto the open ball of radius r centered at the origin, phi maps the closure of B onto the closed ball of radius r, and phi maps B prime onto the open ball of radius r prime. The closure of B is compact. Phi inverse restricted to the closed ball of radius r is a homeomorphism onto the closure of B, and closed balls in Rn are compact, so their image under a continuous map is compact. The key feature is the strict containment. The closure of B sits inside B prime with a positive width annular gap between them. The enclosing ball B prime is not redundant. To construct a smooth function that is identically 1 on the closure of B and identically 0 outside B prime, the transition from 1 to 0 must take place in the annular region between the closure of B and the boundary of B prime. That transition can only be smooth if the annular region has positive width. If the closure of B were all of B prime, there would be no room for the transition and no smooth function with these values could exist. The gap between the two balls is precisely the geometric room that makes the smooth cutoff construction possible. Every smooth manifold has a countable basis of regular coordinate balls. The proof uses a countable smooth atlas, which exists by second countability of M, on each chart domain. U alpha with coordinate map. Phi alpha, consider all preimages of open Euclidean balls with rational center and rational radius r, where there exists a rational radius r prime greater than r, such that the closed ball of radius r prime centered at the same center is still contained in the image phi alpha of U alpha. Each such preimage is a regular coordinate ball. The collection is countable. Countably many charts, countably many rational centers, countably many pairs of rational radii, and it forms a basis for the topology of M. Fix a countable smooth atlas for M. On each chart domain, U alpha with coordinate map, phi alpha, take all preimages, phi alpha inverse of BR of Q, where Q ranges over Qn and R prime range over positive rationals with R less than R prime, subject to the condition that the closed ball of radius R prime around Q is contained in phi alpha of U alpha. The preimage of BR of Q under phi alpha is a regular coordinate ball. The enclosing ball is phi alpha inverse of BR prime of Q, and the coordinate map is phi alpha restricted to that enclosing ball. The collection is countable because it is indexed by a countable atlas, countable rational centers, and countable rational radius pairs. It forms a basis. Given any open U and any P in U, choose a chart containing P, find rational Q and R such that phi alpha of P lies in BR of Q, and BR prime of Q is contained in phi alpha of U, intersected with the chart image, then take the preimage. This gives a regular coordinate ball around P contained in U. On the manifold M, the regular coordinate ball B sits strictly inside a larger coordinate ball B prime. The dashed circle marks the boundary of B prime. The strict containment, the closure of B is a proper subset of B prime, is the defining geometric feature. It guarantees that a positive width annular region exists between the two balls. The coordinate map phi sends B prime diffeomorphically onto the Euclidean ball of radius r prime, and sends B onto the inner ball of radius r. The two radii satisfy 0 less than r prime. The strict inequality is what creates the gap. In coordinate space, the image of the closure of B is the closed ball of radius r, sitting inside the open ball of radius r prime. The annular region between radius r and radius r prime, the purple band, is the smooth transition zone. A smooth cutoff function must equal 1 on the closed ball of radius r and equal 0 outside the ball of radius r prime. The entire transition from 1 to 0 takes place inside this annular band. The width of the band is r prime minus r, which is strictly positive by the condition r less than r prime. The graph on the right shows the radial profile h of the norm of x, the smooth cutoff function in coordinate space. It is identically 1 for norm of x at most r, and identically 0 for norm of x at least r prime. The descent from 1 to 0 is smooth precisely because it takes place over the open annular interval from r to r prime. If r equaled r prime, the function would have to jump discontinuously at the single radius r. No smooth function can do that. The regular coordinate ball definition engineers exactly this positive gap. If the two radii coincide, r equals r prime, then B and B prime are the same ball, the annular gap has 0 width, and no smooth transition zone exists. Any function that is 1 on the closed ball and 0 outside it would have to be discontinuous at the boundary. The strict inequality r less than r prime is therefore not a convenience. It is the necessary and sufficient condition for the smooth cutoff to exist. Everything in the partition of unity theory rests on the existence of smooth functions that are identically 0 on a half-line. Real analytic functions cannot do this. By the identity theorem, if an analytic function vanishes on any open interval, it vanishes everywhere on its connected domain. C-infinity functions are strictly more general. They need not coincide with their Taylor series. The key example is f of t equal to e to the negative 1 over t for t greater than 0, and 0 for t at most 0. The function f defined by e to the negative 1 over t for t positive and 0 for t at most 0 is smooth on all of R and non-analytic at the origin. Smoothness will be established by induction on the order of differentiation. Non-analyticity follows from the fact that all derivatives at 0 vanish, so the Taylor series is identically 0, yet f is strictly positive for t greater than 0. The key estimate is, for any integer k at least 0, the limit as t decreases to 0 from the right of e to the negative 1 over t divided by t to the k equals 0. The proof substitutes u equal 1 over t. As t decreases to 0 from the right, u increases to positive infinity, and the expression becomes u to the k times e to the negative u. Since the Taylor series for e to the u contains the term u to the k plus 1 over k plus 1 factorial, we have e to the u greater than u to the k plus 1 over k plus 1 factorial for all positive u. Therefore, u to the k times e to the negative u is less than k plus 1 factorial divided by u, which tends to 0 as u goes to infinity. This estimate is the analytic engine of the inductive proof that follows. We prove the lemma in two parts. First, smoothness away from the origin. For t greater than 0, f equals the composition of t maps to negative 1 over t, which is smooth on the positive reals, with the exponential function, which is smooth everywhere. A composition of smooth functions is smooth, so f is smooth on the positive reals. For t less than 0, f is identically 0, hence smooth. It remains to establish smoothness at the origin. We prove by induction that for all k at least 0, the kth derivative of f on the positive reals has the form pk of t divided by t to the 2k times e to the negative 1 over t, where pk is a polynomial of degree at most k. Base case k equals 0, f of t is exactly 1 times e to the negative 1 over t divided by t to the 0, so p0 is the constant polynomial 1. Inductive step. Assume the formula holds for k. Differentiating pk of t divided by t to the 2k times e to the negative 1 over t by the product rule gives two contributions. Differentiating the rational factor by the quotient rule contributes t squared pk prime of t minus 2 kt pk of t over t to the 2k plus 2 times e to the negative 1 over t. Differentiating the exponential contributes pk of t over t to the 2k times 1 over t squared times e to the negative 1 over t, which is pk of t over t to the 2k plus 2 times e to the negative 1 over t. Adding both contributions, the numerator is t squared pk prime of t minus 2 kt pk of t plus pk of t, which we call pk plus 1. Its degree is at most k plus 1. With the formula for fk at t positive in hand, we prove fk at 0 equals 0 by induction on k. Base case, f of 0 is 0 by definition. Continuity at 0 follows from the key estimate with k equals 0. For the inductive step, assume fk at 0 is 0. For t less than 0, fk of t is identically 0, so the left-hand limit of the difference quotient fk of t divided by t is 0. For t decreasing to 0 from the right, the difference quotient equals pk of t divided by t to the 2k plus 1 times e to the negative 1 over t. Each monomial in pk contributes a term bounded by the key estimate, and each such term tends to 0. Both one-sided limits are 0, so fk plus 1 at 0 equals 0. Induction is complete, f is smooth at the origin, and all derivatives there vanish. This smoothness passes to every function built algebraically from f, quotients, sums, compositions, which is how cutoff and bump functions get assembled from it. From the function f, we build smooth cutoff and bump functions. The cutoff function h for an interval with endpoints r1 less than r2 is defined as the ratio of f of r2 minus t to the sum of f of r2 minus t and f of t minus r1. The denominator is everywhere strictly positive. For any real t, at least one of the arguments r2 minus t or t minus r1 is positive. Both cannot be non-positive simultaneously, since that would require t is at least r2 and t is at most r1, which is impossible because r1 is less than r2. Since f of s is strictly positive, if and only if s is strictly positive, at least one of the two f values in the denominator is positive, making the denominator positive everywhere. The function h is therefore smooth on all of R, being a ratio of smooth functions with a positive denominator. The three defining properties of h follow from the fact that f is 0 exactly on the non-positive reals and strictly positive exactly on the positive reals. For t at most r1, the argument t minus r1 is at most 0, so f of t minus r1 is 0, while r2 minus t is strictly positive. So f of r2 minus t is strictly positive. The ratio is therefore 1. For t at least r2, the argument r2 minus t is at most 0, so f of r2 minus t is 0, while f of t minus r1 is strictly positive. The ratio is 0. For t strictly between r1 and r2, both arguments are strictly positive, so both f values are strictly positive, and the ratio is strictly between 0 and 1. The radial bump function h on Rn is defined by composing h with the Euclidean norm. H of x equals h of the absolute value of x for real numbers 0 less than r, 1 less than r2. Smoothness of h on the open ball of radius r1 centered at the origin. The norm of x is less than r1, so h of the norm of x equals 1 by property, I, and h is the constant 1, hence smooth. On Rn minus the origin, the Euclidean norm is smooth wherever it is non-zero, so h equals h composed with a smooth function and is smooth by the chain rule. The two open sets, the ball of radius r1 and Rn minus the origin, cover all of Rn, so h is smooth on all of Rn. The support of h is the closed ball of radius r2. H of x is non-zero if and only if the absolute value of x is strictly less than r2, and the closure of that open ball is the closed ball of radius r2. This is the cutoff function h. For t at most r1, h equals 1. The flat plateau on the left. For t at least r2, h equals 0. The flat zero level on the right. The dashed vertical lines mark the two radii r1 and r2, the boundaries of the transition zone. The shaded region between r1 and r2 is the smooth transition zone. Inside this band, h descends smoothly from 1 to 0. The descent is governed by the ratio of f values and is smooth because f is smooth and the denominator is everywhere positive. Outside this band, h is constant, identically 1 to the left, identically 0 to the right. In 2 dimensions, the same idea gives the radial bump function h of x equals h of the norm of x in 2 dimensions. The inner circle marks the ball of radius r1, where h equals 1. The dashed outer circle marks the ball of radius r2, the boundary of the support. The gradient fill makes the radial structure visible. The disk is brightest at the center, where h equals 1, and fades to 0 at radius r2. The arrow confirms that the 2D disk is obtained from the 1D profile simply by replacing the variable t with the Euclidean norm of x. Rotational symmetry follows immediately. H of x depends only on the distance from the origin, not on direction. The support of h is the closed ball of radius r2. H of x is non-zero exactly when the norm of x is strictly less than r2, so the set where h is non-zero is the open ball of radius r2, and its closure is the closed ball. This closed ball is compact, and it is the closure of a regular coordinate ball when h is transplanted to the manifold via a chart map. One bump function isn't enough for a global construction. Combining many requires a family with compatibility conditions, the definition of a partition of unity. Given a topological space M and an indexed open cover X alpha, indexed by a set A partition of unity subordinate to this cover is an indexed family of continuous functions psi alpha from M to R, satisfying 4 conditions. First, each function psi alpha takes values in the closed interval 0 to 1. Second, the support of psi alpha is contained in X alpha. Each weighting function lives inside the corresponding chart domain. Third, the family of supports is locally finite. Every point of M has a neighborhood that meets only finitely many of the supports. And fourth, at every point of M, the psi alpha sum to 1. When M is a smooth manifold, the partition of unity is smooth if each psi alpha is a smooth function from M to R. Condition 3 ensures that the sum in condition 4 has only finitely many non-zero terms near each point, so there is no convergence question. The sum is locally a finite sum of continuous functions and hence continuous. If each psi alpha is smooth and the supports are locally finite, the key principle established earlier guarantees the sum is smooth everywhere on M. Condition 4 gives the weighted average property. At each point, the weights are non-negative and add to 1. So the weighted combination of any local data is a convex combination. This is precisely why taking a weighted average of positive definite bilinear forms with these weights produces a positive definite bilinear form. These conditions say what a partition of unity must satisfy, not that one exists for a given cover. That existence is what remains to be shown. For any smooth manifold M and any indexed open cover X alpha indexed by A, there exists a smooth partition of unity subordinate to the cover. The proof has 4 steps. Step 1. Produce a countable, locally finite refinement of the cover by regular coordinate balls. By the proposition on countable basis of regular coordinate balls, M has a countable basis B of regular coordinate balls. Applying the paracompactness theorem to the open cover X alpha with basis B gives a countable, locally finite open refinement Bi indexed by the positive integers, with each Bi a regular coordinate ball contained in some X alpha. By part A of the lemma on locally finite collections, the closures of the Bi also form a locally finite collection. Step 2. For each I, construct a smooth function fi with support exactly equal to the closure of Bi. Since Bi is a regular coordinate ball, there is an enclosing coordinate ball Bi prime with radii Ri less than Ri prime and coordinate map phi I mapping Bi prime diffeomorphically onto the open ball of radius Ri prime in Rn. Let Hi be the radial bump function on Rn with inner radius Ri and outer radius Ri prime. Define Fi of P to be Hi of phi I of P for P in Bi prime and 0 for P in M minus the closure of Bi. These two definitions agree on the overlap Bi prime minus the closure of Bi. On that region, Hi of phi I of P is 0, matching the second definition. Smoothness of Fi is verified by covering M with 2 open sets. On the open set Bi prime, Fi equals Hi composed with phi I, which is smooth by the chain rule. On the open set M minus the closure of Bi, Fi is identically 0, hence smooth. These 2 open sets cover all of M because Bi prime contains the closure of Bi. For the support, Fi of P is non-zero if and only if the norm of phi I of P is less than Ri. That is, P lies in Bi. Therefore, the support of Fi is the closure of Bi. Step 3 normalizes the functions fi into a partition of unity. Define f of p as the sum over all I of fi of p, since the supports of the fi equal the closures of the bi's, and the collection of closures was shown to be locally finite in step 1, the key principle guarantees that f is smooth on M. The function f is everywhere strictly positive. For any point p in M, p lies in some bi, and fi of p is strictly positive for that I. All other terms fj of p are non-negative, so f of p is strictly positive. Define gi of p as fi of p divided by f of p. This is smooth, fi is smooth, f is smooth, and f is everywhere positive. The functions gi satisfy 0 at most, gi at most 1, and their sum at every point equals f of p divided by f of p, which is 1. Step 4 reindexes to match the original cover. Since the collection bi refines the cover x alpha, for each I we may choose an index a of I in A such that bi is contained in x alpha with alpha equal to a of I. For each alpha in A, define psi alpha as the sum of gi over all I with a of I equal to alpha. If no I satisfies a of I equal to alpha, set psi alpha identically 0. The collection of supports of gi contributing to psi alpha is a subcollection of the locally finite family of closures of bi's. Any subcollection of a locally finite collection is locally finite, so by the key principle, psi alpha is smooth. All 4 axioms of the partition of unity definition are now verified. For non-negativity, each gi satisfies 0 at most gi at most 1, so psi alpha is non-negative and at most 1. For the support condition, the support of psi alpha equals the union over all I with a of I equal to alpha of the closure of bi by part b of the lemma on locally finite collections. Each closure of bi is contained in bi prime, which is contained in x alpha. For local finiteness, any point of M has a neighborhood meeting only finitely many closures of bi's, hence only finitely many alphas. For the partition condition, the sum over all alpha of psi alpha equals the sum over all I of gi, which equals 1 identically. The family psi alpha is a smooth partition of unity subordinate to the cover x alpha. 3 overlapping bump functions sum to a strictly positive total. Dividing each one by that sum normalizes them, so the rescaled functions gi add up to exactly 1 at every point. Specializing this construction to the simplest cover, a set and the complement of a closed set it contains yields a single bump function equal to 1 on that set. The existence theorem is now applied to produce smooth functions that are identically 1 on a prescribed closed set and vanish outside a prescribed open neighborhood of that set. A bump function for a closed subset, A of M, supported in an open set, U, containing A is a smooth function, psi from M to the reals, that satisfies 3 conditions. Psi is between 0 and 1 everywhere, psi equals 1 on all of A, and the support of psi is contained in U. The question is whether such a function always exists for any closed A and any open U containing A. Smooth bump functions always exist on smooth manifolds. Set U0 equal to U and U1 equal to M minus A. Since A is closed, its complement M minus A is open, so both U0 and U1 are open subsets of M. Every point of A lies in U0 because U contains A. Every point not in A lies in U1 because M minus A contains every such point. Therefore, U0 and U1 together cover all of M. By the existence theorem, this 2-element cover has a smooth partition of unity. Smooth functions psi 0 and psi 1, each taking values in 0 to 1, summing to 1 everywhere, with psi 0 supported in U0 and psi 1 supported in U1. The function psi equals psi 0 satisfies all 3 required properties. First, psi is between 0 and 1, by axiom I of the partition of unity. Second, the support of psi is contained in U0 equals U by axiom 2. Third, psi equals 1 on A. For any p in A, p does not lie in M minus A, which equals U1. Since the support of psi 1 is contained in U1, and p is not in U1, p is not in the support of psi 1, so psi 1 of p is 0. By axiom, if psi 0 of p plus psi 1 of p equals 1, so psi0 of p equals 1. Since p was an arbitrary point of A, psi is identically 1 on all of A. The existence theorem converts any pair of a closed set and an open neighborhood into a smooth bump function. And the same two-element cover argument applies when the closed set is the domain of a smooth function whose values must be extended globally. The extension lemma gives that result. We revisit the two-element cover construction now as a concrete picture. Here is the manifold M drawn as a strip with a closed subset A marked in the middle and an open set U containing A shown with a dashed outline. The second set of the cover is U1, the complement of A in M. Because A is closed, this complement is automatically open, and together U and U1 cover all of M. From the existence theorem, this cover admits a partition of unity, and we focus on the function psi1, subordinate to U1. Since the support of sec1 is contained in U1, and U1 is disjoint from A, psi1 must be identically 0 on all of A. The flat segment you see here is forced by the support condition. We now set psi0 equal to 1 minus psi1. Wherever psi1 vanishes, psi0 equals 1. And since that is exactly what happens on A, psi0 is identically 1 there, which is the bump function property. We can check this directly at a point P inside A. There psi1 of P is 0 and psi0 of P is 1, so their sum is 1, confirming the partition of unity identity at this point. And the same reasoning holds for every point of A. The same closed set argument, generalized from constants to functions, is exactly what the extension lemma proves. Any smooth function defined on a closed subset of M extends to a smooth function on all of M, with the extension supported inside any prescribed open neighborhood of the closed set. Smooth on a closed subset. A means the following. For each point P in A, there is an open neighborhood WP of P in M and a smooth function from WP to RK that agrees with F on the intersection of WP with A. This is the notion of local extendability at each point. Not that a single global extension already exists, but that F looks like a smooth function in every coordinate neighborhood of every point of A. The proof begins by forming a suitable open cover of M. For each P in A, intersect the local extension neighborhood WP with U to get an open set WP prime. This is open, contains P, is contained in U, and admits the smooth extension F tilde P. Also set W0 equal to M minus A, which is open since A is closed. Every point of A lies in WP prime for its own P. Every point of M not in A lies in W0. So the collection of all WP prime for P in A together with W0 is an open cover of M. Applying the existence theorem to this cover gives a smooth partition of unity psi lambda subordinate to it. For each index lambda in the partition of unity, if the support of psi lambda is contained in some WP prime, define H lambda of x as psi lambda of x times F tilde P of x for x in WP prime, and 0 for x outside the support of psi lambda. This is well defined. On the open set WP prime, H lambda equals psi lambda times F tilde P, which is smooth. On the open set M minus the support of psi lambda, H lambda is identically 0, which is smooth. On the overlap of these two open sets, where x is in WP prime but outside the support of psi lambda of x is 0, so psi lambda times F tilde P is also 0, agreeing with both definitions. If instead the support of psi lambda is contained in W0 equals M minus A, define H lambda to be identically 0. Set F tilde equal to the sum over all lambda of H lambda. By local finiteness of the supports of psi lambda and the key principle, F tilde is smooth. For any x in A, each lambda whose support is contained in W0 contributes 0 to F tilde at x, because x does not lie in W0 equals M minus A. For lambda whose support is contained in WP prime, H lambda of x equals psi lambda of x times F tilde P of x, since x lies in A and WP prime intersected with A, and F tilde P agrees with F on that intersection. F tilde P of x equals F of x. So H lambda of x equals psi lambda of x times F of x. Summing over all contributing lambda, F tilde of x equals F of x times the sum of psi lambda of x over all contributing lambda, and since the partition functions sum to 1 overall and the W0 terms contribute 0 at x, the sum of psi lambda over all lambda is 1. Therefore, f tilde of x equals f of x for all x in A. This lemma is one instance of a pattern that recurs whenever a local construction must be assembled globally. Partitions of unity are the primary local-to-global mechanism in smooth manifold theory. The pattern is always the same. Define an object locally on each chart, then form a weighted sum using a partition of unity. Local finiteness of the supports makes the sum smooth, and the partition condition, the weights summing to 1, allows the weighted sum to inherit structural properties, such as positive definiteness, from the local pieces. The entire development rests on a chain of 5 facts, each depending on the previous. Step 1. The function f of t equal to e to the negative 1 over t for t positive and 0 for t non-positive is smooth on all of R with all derivatives vanishing at the origin. This requires the inductive argument using the key estimate on exponential decay, the estimate that e to the negative 1 over t divided by t to the ka tends to 0 as t decreases to 0 from the right for every non-negative integer k. Real analytic functions cannot possess this property. Smooth non-analytic ones can. Step 2. From f, one constructs a smooth cutoff function h that equals 1 on the half-line to the left of R1 and equals 0 on the half-line to the right of R2, with a smooth transition on the interval between R1 and R2. The construction is a ratio in which the denominator is forced to be positive by the fact that the two arguments in the numerator and denominator cannot simultaneously be non-positive. Step 3. Composing h with the Euclidean norm gives a smooth radial bump function on Rn that equals 1 on the closed ball of radius R1 and is supported in the closed ball of radius R2. Placing this bump function inside a regular coordinate ball via the chart diffeomorphism produces a smooth function on M with support equal to the closure of that ball, and normalizing the collection of all such functions by their sum produces the partition of unity. Step 4 combines the bump functions with paracompactness to produce the partition of unity. Paracompactness gives a locally finite refinement by regular coordinate balls. A bump function fi is placed on each ball with support equal to the closure of that ball, and the functions are normalized by dividing by their sum, which is strictly positive everywhere because the balls cover M. Rindexing aligns the normalized functions with the original cover. Step 5 collects the consequences. From the existence of smooth partitions of unity, one derives smooth bump functions for any closed set, extensions of smooth functions from closed subsets, Riemannian metrics on any smooth manifold, a well-defined theory of integration on oriented manifolds, and the Whitney embedding theorem. Each of these results traces back through the chain to the single limit estimate that e to the negative 1 over t divided by t to the k tends to 0. 3 ideas are worth carrying away beyond the mechanics of the proof. First, the entire theory exists only because smooth functions are strictly more flexible than analytic ones. The function e to the negative 1 over t has a 0 Taylor series at the origin, yet is strictly positive immediately to the right of it. A real analytic function could never do this, since its Taylor series would force it to vanish identically near the origin. No analytic bump function can exist for exactly that reason. Every cutoff function, every bump function, and therefore every partition of unity in this presentation is downstream of that single gap between smoothness and analyticity. Second, once that gap is granted, the only topological input the entire construction needs is paracompactness, the existence of locally finite refinements. Everything after that, cutoff functions, normalization, reindexing, is mechanical. Smooth functions glued together using analysis that was settled centuries ago. No exotic topology, no curvature assumption, and no special structure on M is required. This is part of why partitions of unity exist on every smooth manifold without exception. Goodbye, and happy exploring of smooth manifold theory.